I want to give you a little explanation of how a delta kinematic system works. I know it sounds kind of confusing when you're looking at the thing and it's just got these blocks sliding up and down and it's got all these ball joints and the print head is somehow magically moving around. But there's a really simple way to think about it. Today's sponsor, Squarespace.com. So let's say you have your print head right here and you're extruding little bits of plastic right there. And then you've got your vertical supports. You can imagine here's our printed part. Let's say we're making a benchy and we're depositing some material right there. Now we want to continue printing as we move over to this new point. So we want to figure out how to move the print head from here to here. We're going to draw a circle around this point. There's our circle for the first state of that print head, and we'll draw another circle for the red. We're just going to draw another circle just like this. Okay, so we have our two circles, and basically those circles are the same length as the carbon fiber rods that are inside of the printer. What we do here is we just find the intersection point of the circle with the linear rail. And that's where we want to move our block to. We want to move that block right here, and then we can draw in that carbon fiber rod. And likewise over here, draw in our carbon fiber rod. So really it's a circle intersection problem. Mathematically, all you're doing is finding the intersection between the circle and the line, and then you figure out what this coordinate is from the 0 point of this axis. We'll assign y1 to whatever this coordinate is, and we'll assign y2 to whatever this coordinate is. And then if we want to move the print head to this new position, we're just going to do the intersection of these points with the same rails. So just like this. So we're going to move this block down and we're going to move this block up in order to produce that leftward motion. And we can draw in this rod just like this. Doing this type of circle intersection, you can actually figure out what coordinates you need to assign to your y1 and y2 stepper motors to be able to produce any motion or move the print head to any position. Let's just do another example. Well, let's say we want to move the print head over here. So let's say print head, we want to be printing something right in this position. What are we going to do? We're just going to draw the circle around this point. Here's our intersection point. And then here's our other intersection point. And this is what our rods are going to look like. Just like that, you can figure out any motion or any position inside of this delta kinematic mechanism. When you're really far over to the side here, this motor is having to move a lot and it's almost at a right angle. And once you get to a 90-degree angle with this joint, you lose control of what's happening with the system. You can't move any further to the left once that's at a 90-degree angle. And even when this is at a really shallow angle relative to the horizon, you lose a lot of ability to accelerate. So towards the edges, you end up with some weird stuff. What's the solution to this? Well, you either want to move your rails in closer together or make these rods longer. Like, let's just draw a bigger circle here. This bigger circle is what we would have if these rods were just a little bit longer. So our intersection point for this axis moves up here, and then our intersection point for this axis moves up here. And this is what those extended rods would look like. You would regain position control if you were to make those rods longer. So with these type of delta kinematic systems, they're not all that complicated once you understand the math and the geometry behind them. Oh, and if you want to learn a little bit more about this stuff, I'm going to post a companion article to this little explanation on my website, which is hosted on squarespace.com.
This time I tried their built-in AI assistant, which can help reword difficult paragraphs or write entire articles for you. They're always adding new tools and features to help you be as productive as possible when working on your website. So head over to Squarespace to start your free trial using the link in the video description below. When you're ready to launch your website, go to squarespace.com/NathanBuildsRobots for 10% off.
Thanks Squarespace for sponsoring this episode, and yeah, let's keep on erasing this thing. With this red example, you can see there's this intersection up here, and then if you look down here, there's actually another intersection with the circle down there. Likewise, on the other side, there's a second intersection point. So you're just gonna write some logic to ignore this bottom intersection and just assign the linkage to move to this position. But you could equally have the link down here and down here, and that would produce the same position with the same length linkage and the same rails. So, you know, that's just one of those interesting things. All right, so how does this relate to our three-dimensional printer where we've got three axes? Well, we just abstract this idea up into one higher dimension. So instead of dealing with circles, we're dealing with spheres. So we're gonna draw our little FLSUN. Here's our little print area. We've got one pillar here, and one pillar here. And we'll just tie those together up top, and they're tied together down here structurally. When we want to move our print head to the middle right here, let's say we want to print our little benchy down here, we're just going to draw a sphere. So, you know, it's kind of difficult to draw a sphere on a whiteboard. Maybe if I was in a CAD program, I'd be able to do this a little bit better. But with our sphere, we're basically going to have an intersection point like right here, and right here. And actually, if we're in the center point and all of these rods are the same length, then these should all be at the same Z height. Our rods would be like that, and that. If we wanted to move this up, then that sphere would move upwards and all the intersection points would move upwards. If we wanted to move this to the right, then we would redraw our sphere over there. Let's say it looks something like this. So our intersection point is going to be lower on this side, it's going to be higher on this side, and it probably will only change a little bit on this side. Maybe it'll move up just a little bit. But then our linkages would look like that. Okay, so that's your crash course in how these delta kinematic systems work. They're not super complicated, but they're a type of mechanism called a parallel mechanism, which is opposed to a serial mechanism. Basically like a regular robot arm. You can think of this as ground. You got, you know, one link here, another link here, another link here, and then let's say you've just got like a gripper. This is a serial mechanism where you've got one angle, two angles, and then three angles. I don't know if you assign random Greek letters to them to describe where this end effector is going to be. Versus on this one, instead of these being one after another in serial, they're all in parallel. So they're all affecting the position of the end effector through some complex mathematical equation that's based on this sphere intersection problem. Okay, so what do you think? Was that kind of cool to learn about it? Do you understand a little more about parallel kinematic mechanisms and these delta printers? Some interesting things to think about is, in this case, we don't have a single sphere. We would actually have multiple spheres based on where the attachment points on the hot end are. So, you know, they don't all conjoin into a single spherical joint. They're actually at three separate positions. So it's actually three separate sphere intersection problems that are intersecting their own arm. Also, another interesting thing to think about is if we turn this into a square with 4 vertical bars instead of 3, you would do the same spherical intersection problem. You would just be able to add an extra link in there, and that would increase the stiffness, but you know, that increases the cost of the system without giving you any more control over the position of things. So that's something that you could do if you had like a system that had to be super precise or something. You could add a fourth column in there, or you could add as many as you wanted. You could have 100 of these ball joints attached to the same hot end, and as long as you're lining everything up mathematically, you could move them in unison. All right, I'm not gonna get too much further into the math and the geometry of these mechanisms. Although I do want to tell you one last thing is, there's a way to make a delta mechanism that just uses 2 linear rails, 3 blocks, and some system of different length rods to make a 3D printer like this. You would just have, let's say all 3 of these rods were different lengths. You'd have one sphere intersection for your first rod, another sphere intersection for your second rod, and then another spherical intersection for your last rod there. So you could make a delta printer that just had 2 rails and had all of the axes behind the print bed. But the reason why they'll usually position them equilaterally around the printer is because it makes the math easier and all of the sub-assemblies are identical, and that ends up usually being the stiffest when you equally space things out. When you do something like this, having the end effector way out front outside of the middle point of these little things, it basically makes it harder to control that point precisely. There's all sorts of studies and trade-offs that you can do with this stuff, but yeah, I'm seriously going to stop now.